We're going to take a look at some errors and artifacts that can appear in radar data, including how you can identify them and how you can address them in your analysis. First, let's dive into some of the issues that can arise with data both near and distant to the radar. Radars have distinct limitations on how high they can scan in the vertical. The highest elevation angle that a National Weather Service radar can sample is 19.5 degrees. At just 5 miles from the radar, this corresponds to an altitude of about 11,000 feet, which is only about 20% or so of the depth of typical springtime supercells. Adding more elevation angles would significantly increase the time it takes for a radar to complete a volume scan, which would be extremely detrimental in severe weather scenarios. This brings us to the main problem with analyzing data close to a radar site, the cone of silence, which is a conically shaped region above the highest elevation angle that the radar simply cannot sample. On a two-dimensional radar image, the cone of silence will appear as a circular region free of data surrounding the radar site. This can impede the analysis of storms very near or on top of the radar site. There's not much you can do in these cases except to wait for the storm to fully move out of the cone of silence and use other radar sites if available, as well as other data sources such as satellite imagery to assess the storm.
Seats are currently on sale for our 2027 Storm Chasing Tour. Secure your seat now for this once-in-a-lifetime experience. Link in the description.
Another problem that can plague radar data within about 20 miles of a radar site is ground clutter. Because the radar beam is very near the surface within this range, part of it can interact with non-meteorological objects near the ground, such as buildings, wind turbines, highways, and more. Ground clutter often features high reflectivity and sometimes velocity values that can look like actual storms, sometimes with missing data pixels interspersed. But the key differentiator is that ground clutter does not move. It may sometimes suddenly appear and disappear in the same area, rather than propagate in a specific direction. In addition, because of its non-meteorological nature, ground clutter is often associated with significantly reduced correlation coefficient, and differential reflectivity is often near zero, but can be variable. The ground clutter returns you see here are associated with wind turbine farms near Dodge City, Kansas, and are a permanent fixture around the Dodge City radar site. The degree of ground clutter on radar can increase when a phenomenon called superrefraction occurs. The speed of the electromagnetic waves emitted by radars is dependent upon the density of the air through which the waves move. Pressure, temperature, and moisture, all factors in atmospheric density, generally decrease sharply with height. As a result, atmospheric density decreases sharply with height as well, allowing the top portion of the radar beam to move more quickly than the bottom portion. This causes the radar beam to refract or bend toward the Earth's surface the farther it extends from the radar. When the temperature increases with height within a layer of the atmosphere, in other words, when a temperature inversion is in place, or if the decrease in temperature with height is less than is typical, the beam is bent toward Earth's surface more than normal, which is superrefraction. If the beam's curvature matches or exceeds the curvature of the Earth, it's called ducting. An advantage of superrefraction and ducting is that the radar beam can travel much longer distances than normal, helping the radar sample more distant precipitation or storms. However, the beam spends more time closer to the ground and, at long distances, can even intersect the ground, which can increase the intensity of ground clutter echoes. Sometimes, ground clutter can degrade actual meteorological returns, which can muddy the analysis of storms near a radar site. To combat this, you can utilize the tilt or tilts just above the lowest one. This will omit ground clutter returns but still give you a look into the low levels of the storm. Still, the lowest tilt should be used to identify features like tornadic vortices and boundaries. Just like data close to the radar can have issues, so can data far from the radar, particularly at distances greater than 50 to 60 miles. This is because the radar beam spreads out the farther it extends from the radar. Think about shining a flashlight in a dark room. The light spreads out and becomes more diffuse the farther it gets from the flashlight itself. The same thing happens with the radar beam. For every 10 miles the beam travels, it spreads out approximately 1,000 feet, so at 120 miles from the radar, the beam is over 2 miles wide. This has significant implications on the resolution of the echoes returned to the radar. Many storm-scale features easily seen in data close to the radar, such as hook echoes and boundaries, are often muddled or even fully masked at long distances from the radar. In addition, because Earth's surface is curved, the radar beam gets farther and farther from the ground the more it extends outward from the radar, aside from instances of ducting. At a distance of 100 miles from a radar site, the beam is about 10,000 feet above the surface, and at a range of 200 miles, it's about 29,000 feet above the surface. Therefore, the beam overshoots the lower portions of storms at long distances from the radar, making the analysis of low-level features like mesocyclones, tornadoes, and boundaries nearly impossible. This is especially the case in radar holes, which are areas that feature little to no low-level coverage from any radar. This map shows the radar coverage at 4, 6, and 10,000 feet above ground level, indicated by the yellow, gold, and blue shading respectively. Areas in white receive no radar coverage below 10,000 feet. You can see that several areas that frequently experience severe weather lack robust low-level radar coverage, including parts of New Mexico, Texas, southeast Oklahoma, Nebraska, and the Dakotas. Unfortunately, these issues are without a viable solution aside from adding more radars. For example, let's look at the supercell that produced the Barnsdall, Oklahoma EF4 tornado on May 6, 2024, using two different radar sites. First, we'll look at the supercell from the Tulsa radar site KINX, located about 40 miles from the storm. Note the well-defined hook echo and rear flank downdraft gust front boundary, evident in both reflectivity and velocity data, as well as the strong tornado vortex signature. Now let's switch to the Oklahoma City radar KTLX, located about 90 miles from the storm. The aforementioned features are no longer evident, and the storm looks a lot more amorphous. This is a result of the beam spreading out significantly at this range compared to that of the Tulsa radar, degrading data resolution. Also, the velocity couplet is a bit broader as well. In this case, the beam was about 9,400 feet above the surface, so we're only getting a look at the mid-level mesocyclone and are unable to make any clear determinations about any tornadic activity from just the reflectivity and velocity data. Intense tornadoes can loft debris tens of thousands of feet into the atmosphere, so in these situations, correlation coefficient may still be helpful. Alright, let's now take a look at some specific artifacts and errors that can show up in radar data. Earlier we talked about ground clutter, which is one of many non-meteorological phenomena that can occur. Biological scatterers, namely insects, birds, and bats, can also appear on radar. The large region of slightly enhanced reflectivity that tends to envelop radar sites during some evenings is called bloom, and it's due in part to all of the insects that fly around at night. Birds and bats will often produce uniform rings or circular areas of slightly enhanced reflectivity emanating outward from a point. Most of the time, biological scatterers will produce reflectivity values less than 20 dBz, but occasionally they can exceed 30 or 40 dBz. Typically, they're associated with uniformly high differential reflectivity, but low correlation coefficient. During training exercises, military aircraft sometimes emit strips of aluminum called chaff, which is highly reflective and hides the aircraft from enemy radar. Chaff can be easily mistaken for precipitation, as it often takes on the shape of a storm on radar and moves just like a storm does as well. If an apparent storm or area of precipitation seems unusual given its location or background environment, be sure to check if there are any military bases in the area, and use correlation coefficient to confirm whether or not the echoes are legitimate. Chaff is associated with significantly decreased correlation coefficient akin to other non-meteorological targets. Smoke plumes from large fires can also appear on radar as areas of slightly enhanced reflectivity that spread downwind from a single stationary point. They also feature extremely low correlation coefficient. While most radars are situated in areas that provide a clear view to the sky in all directions, some suffer from beam blockage, which is when things like buildings, trees, hills, and mountains obscure part of or even the entire beam in certain directions. Beam blockage can wreak havoc on storm analysis because it can cause the intensity of echoes to be drastically reduced, or, even worse, it can hide part or all of a storm from the radar's view. In these situations, using an elevation angle higher than the lowest one can help alleviate the beam blockage issue, and in extreme cases in which several tilts are affected, the composite reflectivity product can help you see the storm more effectively. For example, the Tucson, Arizona radar site KEMX is located in the mountains near the city, causing significant beam blockage issues particularly to its south and southwest. Focusing on this area, notice how the base reflectivity data shows little in the way of robust convection, but if we switch to composite reflectivity, we see several intense thunderstorms occurring. The next artifact is one that we introduced in our discussion of pulse repetition frequency and a quantity called the maximum unambiguous range, which is the maximum range within which a transmitted radar pulse can be scattered and received before the next pulse is transmitted. If a radar emits a pulse before the backscattered energy from the previous pulse is received, the backscattered energy will make it back to the radar, but the radar is unable to accurately tell which pulse it came from and how far the target is from the radar. This is called range folding, and it can have a significant impact on the readability of radar data. Thankfully, National Weather Service radars are equipped with methods to combat range folding, namely alternating between two different electromagnetic waveforms that each have different PRFs for the lowest few elevation angles. This almost always alleviates range folding in reflectivity data. However, radial velocity measurement relies on a single PRF, so range folding issues often plague velocity data. Range-folded pixels will appear as purple in most radar programs, indicating that the data cannot be recovered for those pixels. On the same token, every radar assumes that any returned echo is from the most recent pulse it emitted. If the radar receives backscattered energy from the pulse previous to the most recent, it thinks the return is from the latest pulse and, therefore, plots it closer than where it really is. These are called second-trip echoes, which manifest themselves as elongated streaks of echoes emanating outward from the radar along radials, where no active weather is occurring. Precipitation particles scatter most of the electromagnetic energy from a radar beam in all directions, including back toward the radar. However, a fraction of that energy is absorbed by the particles themselves. This can cause the radar beam to become less intense the more particles it passes through as it extends outward from the dish, a phenomenon called attenuation. The amount of energy that's absorbed and, therefore, the amount of attenuation depends on the intensity of the precipitation and the wavelength of the pulse. If a radar beam passes through a light shower, the attenuation will likely be fairly minimal, but if it passes through, say, the heavy precipitation core of an intense supercell, the attenuation will be much greater, often erroneously decreasing the apparent intensity of more distant storms in line with the supercell's core. Also, shorter wavelength pulses are more susceptible to attenuation. This is why terminal Doppler weather radars and mobile radars are best suited for close-range weather observation. They use a shorter wavelength than National Weather Service radars and, in turn, suffer from greater attenuation issues. In this example from the TOKC terminal Doppler radar in Oklahoma City, located at the Pink Star, the beam was shooting through very heavy rain to the radar's immediate west. The storm farther to the west was of equal intensity to the band of heavy precipitation, but notice how reflectivity within the storm was significantly lower than that of the band. This is a product of attenuation as the beam traveled through the initial heavy rain band. Up to this point, we've described the radar beam as being focused within a single lobe of energy. However, this is not exactly the case, as radars have an imperfect radiation pattern. This creates weaker auxiliary lobes of energy that occur both in the horizontal and vertical, called side lobes, that can sometimes impact data quality, particularly in the velocity product. Most of the time, the radar data we see is dominated by returns within the main lobe, and these side lobes have little impact on the overall output. But sometimes returns within side lobes dominate the total signal, as in this example here, where the side lobe features a much greater preponderance of hydrometeors, including rain and large hail, than the main lobe. This induces an artifact called side lobe contamination. Again, most of the time, side lobe contamination is not an issue, but it can be a major problem in regions with sharp changes in reflectivity, either horizontally or vertically. As it relates to storm chasing, a textbook example of this is in the inflow region of a supercell, which often features a strong vertical reflectivity gradient. Side lobe contamination manifests itself in velocity data as an erroneous area of rotation that can mimic a strong mesocyclone or tornado vortex signature, but is displaced from where rotation should be located within the storm. In other words, a side lobe contamination-induced couplet will not be co-located with a supercell's hook echo or rear flank. Side lobes are also the reason why ground clutter occurs, as they interact with objects at the ground rather than the main lobe. Let's take a look at an example. At first glance, it appears that a tornado may actually be in progress. We have a bona fide supercell, complete with well-defined hook echo and a strong, tight velocity couplet. However, upon closer inspection, notice how the velocity couplet is located in the inflow region of the storm, much closer to the edge of the forward flank. This is a classic sign of side lobe contamination. If this was a tornadic couplet, it would be located back in here, coincident with the tip of the hook echo. Also, note the lack of reflectivity in the vicinity of the couplet, but as we go up to the next tilt, we see strong reflectivity in this area, indicative of a strong vertical reflectivity gradient. This is evidence that the side lobes of the beam at the lowest elevation angle were encountering a much greater concentration of hydrometeors than the main lobe.
Seats are now available for our 2027 storm chasing tour. It's 8 full days of storm chasing, and the coaches on this tour are Trey Greenwood, Cameron Nixon, Kyle Gillette, and Hunter, folks. It is a lineup filled with absolute all-stars, and if you've ever wanted to go out storm chasing but you're not quite sure, or if you're just looking for a once-in-a-lifetime experience, this is definitely something you'll want to check out. Click the link in the description below for more information.
Here's another example. Once again, we have a classic supercell with a well-defined appendage and a very strong velocity couplet. However, the couplet is located in the clear air well out ahead of the appendage, so this is side lobe contamination. In some cases, side lobe contamination can occur in tandem with legitimate rotation. In this example, we see two potential areas of rotation. The one on the left is co-located with the supercell's appendage, evidence that it's a legitimate rotational couplet, while the one on the right is side lobe contamination, situated in the storm's inflow region just south of the forward flank. You can see how easy it is to be fooled by one of these erroneous couplets, so always make sure that the velocity couplet in question is real when you're analyzing radar data. This graphic from Betcher and Bentley 2022 gives a good workflow for diagnosing whether or not a circulation is legitimate or associated with side lobe contamination. Couplets induced by side lobe contamination will be misplaced from the hook echo or rear flank of the storm, typically with weak to no reflectivity in and around the false circulation. Although imposter couplets can mimic a tornado vortex signature fairly well, they also frequently take on a blocky, disorganized appearance that lacks a clear velocity gradient. Finally, there will be a tilt or tilts of enhanced reflectivity above the imposter couplet, which is evidence of ample hydrometeors for side lobes to sample. The final artifact we're going to discuss is called a three-body scatter spike, which is a telltale sign of large hail. When the radar beam encounters large hail within a storm, part of the energy within the beam can get deflected down to the ground, back up into the storm, and then back to the radar. It gets deflected 3 times, hence the name three-body scatter spike. This portion of energy arrives back at the radar slightly later than the original backscattered energy, so the radar assumes that it exists farther along the radial than the storm itself. The result is a spike of low reflectivity that extends along the radial outward from the storm's core. Three-body scatter spikes are also often accompanied by significantly decreased correlation coefficient. On rare occasion, damaging tornadoes can produce a three-body scatter spike as the radar beam deflects off of heavy lofted debris. In these cases, the three-body scatter spike will emanate from the debris ball at the tip of the hook echo in reflectivity.
Remember to check out those links in the description below, and then watch another video.